Welcome to our talk on fast linking numbers for topology verification of Loopy structures. My name is Antti Q, and my co-author is Doug James. Here's a simulation of a chainmail pile. Each sheet consists of interlinked rings. Unfortunately, in this case, a ring falls off and rolls away, because a collision is missed between rings. This error is hard to catch visually. If we simulate something, how do we know it's right? The same Chrono simulator was also used to prepare a chainmail dress for 3D printing by packing it into a box. If we want to use a simulation to aid in manufacturing, how do we verify it's right before printing it out? Here's a simulation we computed of a Kusari chainmail shirt. There aren't obvious visual errors here, but is it correct? Our method can automate this verification process. I will show later that there are actually a few broken links. Let's also look at yarn level cloth modeling. In a Siggraph 2012 paper, this sweater model was relaxed using yarn level simulation. How do we know if it is topologically correct? A common problem in these simulations is pull-through, where yarns illegally pass through each other after missing a collision. For example, the green yarn is on top at first. A pull-through could cause it to pass through the blue yarn, which is not physically possible and alters the topology. How do we know whether the relaxation maintained the yarn pattern topology? Our method will tell you that this relaxed model has an error. So in this work, we propose fast linking numbers, a topological certificate for Loopy structures. Given the model state, our method will compute a linking number certificate before or after processing to enable automatic topology verification. Our other contribution is a systematic evaluation of methods to compute this linking number certificate. In these simulation examples, we compute a certificate during each frame and detect changes in the topology. On the left, as 1,000 free rubber bands slide in the simulation, illegal linkages are marked in red. On the right, we highlight rows of a sweater model that pull through each other. A linking number between two oriented closed curves is an integer that measures how many times one curve winds around the other. It is invariant under link homotopy, which is any deformation where the curves don't cross each other. In fact, during a single yarn pull-through, the linking number must change. This means they can be a topological certificate. Our certificate is a sparse matrix of pairwise linking numbers. There are many ways to compute the linking number, and we will evaluate two of them. The first way is to project onto a plane, and then for every crossing, increment or decrement the result based on the crossing orientation. The second way is to compute the Gauss linking integral. This integral has a magnetostatics interpretation. Suppose the blue loop is a circuit with current I, and the red loop is a test loop. We want to find the current enclosed by the red loop, as that tells us how many times it winds around the blue loop. We can first apply the Biot-Savart law on the blue loop to find the B field at each point on the red loop. Once we have the B field, we can apply Ampere's law to integrate it over the red loop, giving us a linking number. Many works in the past addressed geometric verification by using determinant-based tests. Many of these tests are discrete because they verify individual states have no interpenetration. Continuous collision detection verifies an entire trajectory is collision-free. There are trade-offs between continuous and discrete tests. Our method is a discrete test in that it checks individual states of an animation. In a way, linking numbers can generalize inside-outside tests to loops. Most prior work use a brute force quadratic algorithm. We aim to scale linking number computation to generic large input. Recently, researchers propose using generalized winding numbers to generalize inside-outside tests to curved surfaces and other geometry, and they use Barnes-Hud to accelerate the computation. We explore similar approaches. Our method uses 3 stages to efficiently compute the linking matrix. Given an input set of loops, we first compute a list of potentially linked pairs of loops. Then we carefully discretize the loops into polylines, and finally we process the polylines to compute a sparse triangular linking matrix. This is the final certificate. Two structures with the same linking topology would have the same matrix. Stage 1 is a potential link search. We first compute bounding boxes and build a bounding volume hierarchy. Because two loops with separated bounding boxes do not link, we can just output the pairs of intersecting bounding boxes as a list of potential links. This culls the number of potential pairs greatly. For example, with the chainmail, if R is the number of rings, the number of potential pairs goes down from R squared to R. The second stage is discretization to convert the curves into polylines. We start with a segmented curve and compute 3D bounding boxes around each segment. At this stage, we detect any zero-lane segments because our method does not handle them, so the user can throw them out and retry. For any boxes that overlap with those of other curves, we simply subdivide their segments into two and then repeat this procedure until no more boxes overlap. This procedure terminates quickly if the curves do not intersect, and if they intersect, the boxes shrink to machine epsilon in size and we simply return with an error. After we finish the subdivision, we deform each curve segment into a line segment so they're ready for the next step. Stage 3 is the actual computation of linking numbers. There are many possible ways to do this, and this is where we hold our bake-off, exploring each method and its advantages. We'll first discuss counting crossings, then we'll discuss direct summation of the linking integral, followed by the fast multipole method, and finally Hud integration. The next few slides will go into detail on these. The first method is counting crossings. We first project line segments onto a 2D plane using a regular projection. A regular projection is a projection that avoids these two degeneracies, where a vertex overlaps another segment or multiple intersections are coincident. If the loops have a lot of points, we build a 2D BVH of the segments from one curve. We then iterate the other curve in parallel and use the BVH to detect intersections. At every intersection, we can increment or decrement the result based on the sign of the crossing. The advantages are that it is simple, parallel, and fast for most input. The disadvantage is that the quality of projection can be a potential concern. The second approach is doing an Embody direct summation of the linking integral. We start with the loops as polylines, and we want to compute the linking numbers. We can rewrite the integral as a double sum of integrals over line segment pairs. We call each line segment pair value lambda ji. This will correspond to the integrand evaluated over a single pair of segments, in this case between the red and blue segments, and it has a closed form expression. The expression comes from the sine solid angle formula, which involves evaluating two arctangents and is well defined when the curves do not intersect. We evaluate this double summation in parallel on the GPU and the CPU. Interestingly, generalized winding numbers also uses the same solid angle expression. Furthermore, the two numerators are actually the same, so we reuse this triple scalar product in our implementation. The advantages are that it's fast on small loops and parallelization scales really well. The disadvantage is that it's slow on large loops because it's a quadratic time algorithm. The third method is the fast multipole method. It is a standard method for Embody Laplace problems, and there are many ready-to-use FMM libraries. We use fast multipole as a black box tool to mass evaluate the Biot-Savart integral. Denote the blue loop as a source and the red as a target. The method basically takes as input a list of source points, source currents, and target points, and outputs B fields along the target loop. We then use the Ampere's law to get the linking number by summing along the target loop. To reduce the midpoint sampling error, we added an exact finite segment correction for closed segment pairs. See the paper for more details. We tested two FMM libraries. The advantage of FMM is that it's efficient on large examples. However, the disadvantages are twofold. First, fast multipole has a large overhead that scales poorly except on the largest problems. And second, FMM repeatedly evaluates a field at every target segment for every loop pair that a target loop participates in. This could be unnecessary work when target pairs segments are far away from the other curve. See the paper for more details. The last method is Hud integration. It's a popular n-log-n method for evaluating Embody problems. Once again, we start with the loops as polylines, and we want to compute linking numbers. We pre-build a BVH tree of segments for each loop, and pre-compute their multipole moments. Here I illustrated one node from a red loop, and two nodes from a blue loop. During evaluation time, we traverse both trees from the root down, and evaluate nodes in one loop against the other loop. The beta parameter is the threshold for deciding if nodes are in the near or the far field, based on how far apart they are compared to their size. For nodes in the far field, we just use the far field multipole expansion to estimate their contribution. When they're in the near field, we traverse their children. For leaf nodes, we use the direct expression for a pair of line segments. We also compute an error estimate while traversing the tree and increase beta if the error is too large, and also we parallelize it. The advantage of Barnes Hud is that it's fast with a lower overhead than the fast multipole method. The disadvantage is, like with counting crossings, it's slow when the loops have long segments. Here are some results. Let's return to the chainmail from the start. We packed the Kusari chainmail shirt into a box to be ready for 3D printing. It is made of rigid curved rings, which we simulate with Bullet in Houdini. The simulation takes 15 minutes to complete. I will show gradually more refined simulations. This simulation takes large steps. The left video shows the simulation, and when violations are detected, the corresponding rings are marked in red in the right video. You can clearly see the many violations in both videos. Here's the simulation I showed you at the start, which takes medium steps. Now you can see that a few links are still broken. Now let's try this again with much smaller steps. We verified that the topology is maintained throughout this simulation. We can also verify yarn models. In the stitch mesh paper, they mentioned 2 ways they could have connected stitches. On the left, stitches could have been arranged in a helix. This structure is knittable, so everything is one long yarn. Our method is designed for closed loops and won't be able to verify this. However, most stitch meshes actually use the structure on the right, which arranges stitches in a cylinder, because it is simpler. In this structure, every row is a closed curve, and we can verify the topology of these yarn models. Here's the relaxed sweater I showed you at the beginning. We can now verify its topology. Knitted stitch structures should not be linked, and the relaxation process attempts to maintain that. In their paper, the sweater took 7 hours to relax. It took under a second for our method to detect these linkages, which are marked in red and indicate violations. Zooming in, we find, for example, that this small green loop only has 3 curves passing through it, when in figure 8, it should have 4 curves. Aha! We see that the relaxation process introduced at least one error, and it should have been reran with a smaller time step size. Here's a yarn level cloth simulation where we take a sweater and drop it onto the ground. I will first show a simulation with topology issues, and then rerun it with smaller steps. Topology violations are marked in red. Here's a rerun simulation with smaller steps. Both simulations are expensive, taking many hours to complete, but only a fraction of a second to verify each visual frame. Here is a stress test simulation, where we twist a knitted tube. Even though it's not apparent, a pull-through has already occurred at this point. Let's rewind a bit and see what our method says. Even though it looks like it destabilized very quickly, because these are small time steps, our method actually detected a violation over 1,000 steps before the destabilization. Now let's drop 1,000 separated rubber bands onto an inclined plane. In a simulation with large steps, violations we detect are highlighted in red. Now we use smaller steps, and our method verifies that it is valid. We can also use cheaper deformers and yarn level simulators. In this example, we started with a vellum simulation of a glove as a deformable TED mesh. We animated our glove yarn model as an embedded deformation, and our method verifies that the topology remains valid. Here's the final render. Our method normally requires closed loops. Can we verify non-closed loops? Yes. A braid consists of two rigid bars with curves attached between them, and we can also verify braids. In this example, we attach a knitted chevron pattern to two rigid bars, making it a braid, and verify its relaxation as the bars are slowly pulled apart. This relaxation uses small steps, and we verified that it is good. When we retry with larger steps, our method detects a pull-through very early. Notice the difference from the good relaxation. Let's look at reparametrization operations. We start with yarn models with Catmull-Rom splines. We decrease the number of control points by resampling along the curves. This deforms the curves, requiring us to verify that the topology hasn't changed. Here are the results as we lower the point count. We mark topology failures in red. Now let's look at curve coordinate compression. Once again, we start with Catmull-Rom splines and simply reduce the precision of their coordinates down to 10 to 24 bits by quantizing them onto a grid. Here are the quantization results. In this model, we detected intersections in the discretization step and exited early, marking it a failure. Let's look at the runtime performance. Note that our GPU is a GTX 1080 from 2016. In most cases, Stage 3, the linking matrix computation, takes most of the runtime. The counting crossings and Barnes-Hud methods are the fastest in most cases, taking advantage of tree structures but still remaining cheap. In particular, the GPU Barnes-Hud shines on large double helix DNA ribbons, taking only 5 seconds on a 20 million segment ribbon. Counting crossings and Barnes-Hud are also efficient in examples with more loops, such as the deformed glove. Here's a plot of the runtimes for the CPU methods. The green axes are the counting crossings runs, and they're the fastest in most cases. The blue diamonds are Barnes-Hud CPU runs, and it's the second fastest in most cases. Both methods finish every example within about a second. We also stress tested with large input. The ribbon has long loops, the thick link has many links, the torus has high linking numbers, and the second wound ball has long segments. As you can see, different implementations win on different stress tests. Also notice the direct summation on the GPU is much faster than the CPU implementation with a 370x speedup. We explored practical algorithms to efficiently certify Loopy structure topology. We found that either counting crossings or Barnes-Hud is competitively fast for most applications. One limitation is that linking numbers are only a sanity check. It's possible for multiple quick pull-throughs to end up with the same linking numbers. The other is that we cannot verify generic open curves, even though we can verify braids. For future work, we recommend simulation rollbacks, verifying curves with finite cross-sections, and expanding our checks to more generic open curves. Thank you for listening to our talk.